Alright, we're going to continue on. We're going to apply what we learned about median, IQR, Q1, Q3. Alright, you guys, pay attention. Okay, box plots are another way to display numerical data. What are the other ways we have to display numeric data? And? No. Dot plots. So already, histograms, dot plots. Okay. Box plots are another way to display numeric data, and they're like a quick summary. Okay, they're like the cliff notes. They don't show a whole lot of detail, but they're good for quick comparisons. Yes?
Are we still in chapter 3?
We're still on chapter 3. Okay. From here on out, we're probably going to do about one chapter a week. Okay, so chapter 3 we'll wrap up today. Next week we'll do chapter 4.
But isn't the quiz chapter 4 included?
No. Quiz next week is only chapters 2 and chapter 3.
Oh,
okay. Right. Is the camera still centered?
Yeah.
You said, please, I'm sorry. No, she's talking about the quiz, chapter 2 and chapter 3 only?
Yes.
Yes. The quiz, I will only cover things I've taught. All the information about the quiz is on the homework page for this week, okay? I list off this week's homework, this week's reading, this week's problems, and the answers, and I also have information on the quiz. I forgot to mention that I also record the lectures and I post them online. You'll find them on the website as well, just under the page lectures. No, I do not have live stream. All right. If we're making a box plot, okay, it's a way to display numeric data. The horizontal axis, what am I going to put along it?
Numbers.
Numbers, right? It's a number line, okay? So I'm going to put a number line here. So, you know, depending on the data that we have, maybe... So maybe we're looking at the ages of people in some club or something. Okay. So you got a horizontal axis. Okay. The box plot is called such because you see a box. There's often a line somewhere in the box. And then you've got some lines extending from the box, and maybe something like that. This is so what a box plot might look like. Okay, so let's actually, let's decompose this box plot. So at the center of a box plot, you've got a box. Okay? The edges of the box Q1 and Q3. This line in the middle, what do you think that is? Q2, or what do we call that? The median. Okay? So Q1, Q2, Q3 define 3 vertical lines that define our box. Okay? The median can be anywhere in between Q1 and Q3. And if the median and Q3 happen to be the same number, then you would only see 2 lines. Okay? Sometimes that happens. The lines that extend from the box, these are known as whiskers. Okay? They extend to the largest and smallest points within what we call fences. Fences are kind of borderlines between what is considered normal and what are considered outliers. Okay, so and anything that's represented with either a star or a circle, a circle or star, those are always beyond the whiskers. These are considered outliers. Okay, I should write potential outliers, but they're considered outliers. Okay, is that all right? All right, so let's look at this box plot that I put, and maybe these are ages of I don't know, something. Okay, ages of people, maybe who ages of people who died from Spanish flu or something. I don't know. I'm just making something up. Okay, I have no idea. That's kind of morbid. All right, what is the median age in this, as represented by this box plot?
28. Oh my god. 30.
The median is this number right here. Okay? So depending on where you are sitting, I don't know, maybe it looks different. I would say the median is like 28. Okay? That would be my guess. Something around there. 27, 28, something, 29. Okay? Is that okay? Yes, no?
Maybe so.
Okay. What is Q1?
20.
Q1 is this value over here.
20.
Great. Q3?
30.
My IQR?
10.
10.
What is the IQR?
Q3 minus Q1.
So 30 minus 20, 10. I get an IQR of 10. What's my maximum?
40.
40. What's my minimum?
7.
7.
8.
7. 8. 6 or 7.
This is my minimum.
4.
Okay, it's the minimum is the smallest number I have, period.
Isn't it like 9?
Maybe 1, 0, I don't know. So my minimum might be 1. Okay? This is the smallest within the whisker, which is different from the minimum. Okay? So this is considered an outlier, but it's still part of the data set. That would be my minimum. Okay, so what's my range? Max minus min. $39.
So you count the outliers.
Yes. In the range you count everything as outliers, okay? We don't have a special name for this. This point right here, this what? The 7, this thing that's around 7, we don't have a special name for it, okay? That's just the smallest point inside the fence. It's the end of my whisker, okay? But we don't have a special name. Is that okay? What percentage of data is bigger than 50? 0%. Do I have any numbers that are bigger than 50? No. 0%. What percentage of numbers are bigger than 20? Just don't shout it out yet. Just think. Think carefully about your answer. What percentage of numbers are bigger than 20? Okay, did you guys think of a number? What's your answer?
40%? No, 60%.
Oh, wait.
Oh, well,
Okay.
is it 60%?
What is 20? What number is 20?
75%?
75% is bigger than 20, okay? Why? What is 20? 20 is Q1, right? Q1 is what percentile?
25.
Q1 is the first quartile, which means how much is smaller than Q1? 25%. The first quarter of data is smaller than the first quartile. So Q1 is the 25th percentile. What percentage is bigger than Q1? 75%. Okay? Is that okay? What percent is larger than 20? Okay, 20 is Q1, which is equal to the 25th percentile. So 75% is larger than 20. What percentage of data is between 28 and 30? Don't shout it out.
Oh.
What percentage of data is between 28 and 30? What's in this tiny little slice here? What percent? Don't shout it out. Okay, do you guys have an answer? 25%. 1/4 of your numbers, 1/4 of the people are between 28 and 30. Just in this small slice, okay? So this is a lot of people are between 28 and 30 whenever we're talking about this thing, okay? And that's because that's your median is at 28 in Q3, your third quartile is the 75th is 30, 75th percentile, you got 25% between there and there. Does that make sense? Are there questions on that?
Can you explain it?
Can I explain that? Okay, so 28, this is my median, right? So what percentage of data is smaller than my median? 50%, okay? 30 is Q3. What percentage of data is smaller than Q3? 75%, okay? So I got my 75th percentile and my 50th percentile. How much is going to be in between those two numbers? 25%, okay? Does that make sense? Okay, what percentage of data is bigger than 30? Yeah.
25?
25%, right? Because this is Q3. How much is bigger than Q3? 25%. Okay? So this is a box plot. Is that alright? So if I put questions on a quiz about a box plot, and I ask you questions about Q1 and Q3 and the IQR and what percent's bigger than this or smaller than this, are we going to be okay? Yeah, we might be. We might be. I want to hear yes.
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 All right. Okay. You got some. Well, you have some practice in your homework, okay? And you got the some examples in your book. Alright, so be sure you can identify Q1, Q3, and the IQR from the box plot. Alright. Yes, question?
Can the box plot be moved anywhere in the table, or
What? I'm sorry?
does the box plot move, or is it just like the same plot?
What do you mean by move?
I don't know. Is it just like
It's based on your data.
Yeah, it's based on your data, okay? So, so based on your data, you draw the box plot. So if your data doesn't change, your box plot's not gonna move or change, okay? Because well, I mean, all of these graphs, right? They're based on your data. So based on your data, you produce them, and so then they're not gonna change. Of course, if your data is different, another box plot's gonna look different. Okay? We're gonna have different numbers here. Okay. So now I'm gonna go cover this topic of standard deviation. Okay? Standard deviation is an important concept. It is another measure of spread. Okay? Alright, don't shout out the answer, but I want you to think what the answers might be. We've already learned two measures of spread, two ways to summarize spread. Okay? Well, think of what they are. Okay, don't shout it out. Think of what those measures of spread are. What are they? The range is one and the IQR is the other. Okay? I heard someone say box plot. That's not a measure of spread. That is a graphic display, a way to summarize numeric data. Okay? So, again, conventional wisdom says for skewed data, we prefer the IQR and the range. Okay? And conventional wisdom also says for symmetric data, we prefer the standard deviation. Okay? Again, whether it's skewed or symmetric, you can find the standard deviation. You can find the IQR and the range. But you might prefer one over the other. Okay? Like if you're gonna make a dessert with soda and ice cream, conventional wisdom says you probably prefer Coke or root beer. But can you do it with Sprite? Sure. There's no rule against that. Okay? What's that? A grape soda, yeah. There's no, yeah. Whatever you want, right? So this is America, land of the free. Alright, standard deviation is another measure of spread. Okay? The process in calculating the standard deviation is a little bit more complicated. It's a little more involved. But at the end, you get a number. Okay? And just like when we looked at those families with the different ages and stuff, one family, the range was 4 years, and another family, the range was 14 years. Okay? The family with a range of 14 had more spread than the family with a range of 4. Okay? Or, you know, one family, the IQR was this, and the other the IQR over there was bigger. Okay? The family with the larger IQR, we would say, has more spread than the family with the smaller IQR. Same thing applies for the standard deviation. You got a set of numbers, or a set of ages, or a set of whatever it is. You calculate the standard deviation. If the standard deviation for this set is larger than the standard deviation for this set, we say this set has more spread than this end, okay? So that is it at the most basic level, okay? Standard deviation is a measure of spread. If a data set has a large standard deviation, it has more spread than the data set with a small standard deviation, okay? As long as you keep that perspective, don't worry about the complicated formula. I mean, yes, you will have to learn how to calculate the standard deviation and stuff like that. But the concept of what a standard deviation is I would say much more important than actually finding it. I will ask questions on how to find it. You are responsible for finding it. But the most important part is understanding that it's a measure of spread. Okay? So larger standard deviation means more spread. Okay? That's the basic concept, okay? Alright, so I'm going to put the formula for standard deviation up on the board. Some of you love formulas. I'm not a fan of formulas, actually. But some of you guys love them and use them as crutches. But, you know, I don't recommend that, okay? I recommend the concept a lot more. But if you insist, this is the formula for the standard deviation, okay? S is the symbol that we use for the standard deviation. Okay, this is a formula for the standard deviation. If you don't like formulas, don't worry about it, okay? I will write out the steps for finding the standard deviation, okay? And all of the steps are summarized inside the formula.
Does it say x minus x?
It says x minus x bar, okay? So things, x bar is equal to the mean of the sample, okay? The sample is my set of numbers that I'm working with, right? So x bar is the mean of the sample. X is each number in the sample. The 2 is squared, right? We know what squaring is, and we know what square root. This means to add up. Add up for each number. Alright. What is n?
Number
Number of numbers. Number in the sample. Okay. But again, if you don't like formulas, don't worry too much about that. Okay? Alright. Let's talk about finding the standard deviation. Okay. Number 1. Find the mean. 2. So I'm going to use this term deviation, okay? Kind of give you the idea of why we call this the standard deviation, okay? All right, so let me just take a break and just kind of explain the idea of standard deviation. So standard deviation is a measure of spread, okay? The idea is that we have this idea of what the middle is. We call that the mean. But things aren't always the middle value, okay? Things deviate. Things are different from the middle, okay? Some deviate from it just by a little. Some deviate by a lot, right? So if we think of the average height in the United States, okay? Let's just think of the height of men, okay? Average height in the United States for men is around 5'9", 5'10", okay? Some men are taller than that, some men are shorter than that, okay? Some are very close to 5'9", 5'10", okay? They deviate from that by a little. Some people are way taller, okay? So Lebron James, he's really tall. He deviates a lot from average, okay? Average height. Other people are a lot shorter, okay? They deviate more, okay? But most people are kind of in the middle. So the standard deviation is kind of the idea of what's the typical deviation, okay? Some deviate more than others. So it's like, what's the typical amount of deviation from average, okay? That's the standard deviation. Does that kind of make sense as a concept? Okay? What's the typical amount of deviation from the spread, from the center, okay? So we're gonna find the mean. That tells us where the middle, or the center point is, okay? And we're gonna find the deviations from the mean. Okay. So how do you think we're gonna do that? We just take each number and we subtract the mean from it. Okay, take each number and we subtract the mean. So we do x minus x bar. Take each number and subtract the mean. Okay. And then step 3. So rather than just kind of taking the average of all of these deviations, we do something a little bit funny. Okay, we're going to square all of them, and then we take the average-ish, and then we take the square root of that. Okay. So we're going to square those deviations. Okay. Then I take the average, kind of, by adding them up, and divide. If I took the average, I would divide by n, right? But here I'm doing something a little bit funny. I divide by n minus 1. But don't worry about that. And 6, then we take the square root. Okay. These are the steps that you do to find the standard deviation. Is that okay? All right. And all of those steps are actually captured in this formula, if you want to see how they relate. Okay. Number 1 is finding the mean, so that's right there with the x bar. Finding the deviation is this process of subtracting. Okay, that's step 2. Squaring the deviations, that's represented by the square symbol there. Adding them up, we see that with the summation sign. 5 is divided by n minus 1. And then the square root, we see that at the end, on the outside. Alright, so let's try taking the standard deviation of a set of numbers. Okay, so we had family 1. What were their ages? 1. I don't remember. 1, 5, 9. Whatever. 12, 15. Who cares? Okay. Let's say these were the ages. Okay. All right. Let's find the standard deviation of the ages in family 1. All right. Huh? So this is a new family. Maybe it's a new family, maybe it's the same family. It doesn't matter, okay? These are the ages of the 5 kids right now. We're going to find the standard deviation of the ages in this family. Okay? So first we're going to find the mean. What is my mean?
9. Oh.
How do I find the mean?
Add them all together.
Yeah, I do 1 plus 5 plus 9 plus 12
21.
plus 15. And I divide by 5. Okay, so what does this come out to be?
8.4.
Yeah, okay, I get 42 2 divided by 5. I get my mean to be 8.4. Is that okay? So what's the next step? I'm going to subtract the mean from each number. Okay? So I'm going to do 1 minus 8.4. And what do I get?
Negative 7.
Negative 7.4. And then I do 5 minus 8.4. And what do I get? Negative 3.4. 9 minus 8.4. 0.6. Okay, these are the deviations. Is that okay?
Yes.
All right. So this is step 2. What's the next step?
Add them all.
No. Square the deviations. Square the deviations, okay? So if I do negative 7.4 squared, what do I get?
54.76.
What's that?
54.76.
54.76. Okay? Now be careful. Sometimes if you punch into your calculator negative 7.4 squared, it will report back negative 54.76. That is not correct. Okay? What does it mean to square something? Multiply it by itself, okay? So negative 7.4 squared is what? Negative 7.4 times negative 7.4. Anytime you multiply a negative by itself, you get a positive number, okay? So why would the calculator give you negative 54.76? Because you're not squaring the negative. When you punch it into your calculator and you do negative, if you type it in like this, negative 7.4 squared, this is how the calculator sees it. It sees it as 7.4 squared and then apply the negative, okay? If you're going to use a calculator, just you have to put parentheses around negative 7.4 squared, okay? Or because we know anything squared always ends up being positive, you can just type in 7.4 squared, okay? These will give you the correct answer of positive 54.76. This will give you the incorrect answer of negative 54.76. Okay, this is a common mistake I see students make, so do not make that mistake. Alright, so what are the other numbers that I get when I square them?
11.56.
Okay, 11.56, 0.36, 12.96, 43.56. Excellent. Okay? So that's step 3. I square all of these numbers and I get these. And then I add them up and then I divide by n minus 1. So if I add all of these up, I get a big number.
123.2.
123.04.
Got 2.
Did I do it wrong? No, I did something wrong. 123 point what?
2.
2? Okay, so I added something wrong here. Okay, so I add them up and I get 123.2, and then I divide by n minus 1. So what is my n?
4.
My n is 5, so n minus 1 is 4. So I do 123.2 divided by 4, and I get what?
30.8.
30.8. Okay, and then I take the square root, and I get something else.
5.549. 5.55.
Yeah, 5.55, that's good enough. $30.5498. Yes? Huh? Step 5 is divide by n minus 1, right? Okay, so here I have 123.2. What is my n?
5.
N is how many numbers I have. How many numbers do I have? I got 5 numbers. 5 minus 1 is 4. So I did 123 divided by 4. 123.2 divided by 4. Okay? So that is the standard deviation of family 1. The standard deviation of family 1 is 5.55. Is that okay? Okay, so I want you guys to try this out again and work on family 2. And I don't remember what those ages were. Whatever. Okay, 9, 10, 11, 12, 13. These are the ages in family 2. I want you to find the standard deviation of these 5 ages. Okay, and the answer is 1.581. What's that? Okay, so go ahead and take a minute to figure this out. Alright, how are we doing? We need another minute or are we good? We're good, great. Okay, did we get 1.581?
Yes.
Yes.
Okay, excellent.
Yay,
Should I go over how to do it?
Yes.
Okay, okay. Alright, so what is the mean?
11.
The mean is 11. Is everyone okay with mean is 11?
Yes.
We're good there, right?
9.
Okay, so step 2, I find the deviations from the mean. So I do 9 minus 11, 10 minus 11, 11 minus 11, so I subtract 11 from all of these numbers. Okay? And what do I get? I get negative 2, negative 1, 0, 1, and 2. So far so good? Then what? I square those. I square those numbers. Okay? So what happens when I square those numbers?
4, 1, 0.
4, 1, 0, 1, 4. Good? Great. Add them up. What do we get?
10.
If I add them up, I get 10. Okay? And then, so I divide
By 4.
by n minus 1.
Just 4.
So n minus 1 is 4. And I get 2.5. And then I take the square root. So the square root of 2.5 gives me 1.581. And that is my standard deviation. Okay? So family 2 has a standard deviation of 1.581. Family 1 has a standard deviation of 5.55. So it just confirms what we already knew about these families. Okay? Family 2, the standard deviation or the spread in the ages is less than the spread in the ages than family 1. Okay? How's that? Alright, so here's let's check our understanding here. Okay. What if we look at family 3, okay? And you don't have to write this down, okay? Just imagine, okay? Let's say the ages of family 3 are 30, 31, 32, 33, and 34. What's the standard deviation of ages in this family? Do we know?
Is it 1.5? No. Oh, it is 2.
1.581, okay? So in family 3, they got 5 kids. The ages are 30, 31, 32, 33, 34. What is family 3? Family 3 is just family 2 21 years from now, okay? That's all it is. So will the standard deviation between the ages change 20 and 21 years? No. The spread in the ages is going to be the same 20 whatever years from now as it is now, okay? So adding 20 years to everybody's age doesn't change the standard deviation, okay? So adding whatever, 21 to everyone's age will not change the standard deviation. Okay. Let's look. Here's a similar family. Family 4, okay? Let's say the ages of the kids. You don't have to do any math here. You can write this example down. Is this 9, 10, 11, 12, 15. Okay? Which family has more standard deviation? Family 4 or family 2?
Family 4.
Family 4, why?
There's more variation for the...
Yeah, okay. Family 4 has more spread than family 2, okay? The ages are pretty much the same with the exception of the oldest child. In family 2, the oldest child is only 1 year older than the next one, okay? But in family 4, the oldest child is 3 years older than the next child, okay? So that indicates to us there's a little bit more spread, okay? So this one has a little more spread than family 2. So the standard deviation is a little more, or it's just a little, yeah, it's a little more, okay? So I don't know, I mean, I don't feel like doing all the math here, but we could, right? It's not that much work. We'd have to take the mean and then subtract that off and square and then add them up and divide by n minus 1, take the square root, okay? We can do that. It's a little tedious, but not impossible. And we would get a number that's a little bigger than 1.581, okay? What about this, family 4 versus family 3? Yeah, same thing, right? Okay, family 4 has a little bit more standard deviation than family 3 because we said family 3 is the same as family 2, just 21 years later. Yes?
If you were to use the formula, do you have to put the each of the numbers in the formula and do it over and over again?
Okay. Yeah, this is why I don't like encouraging formulas, okay? This formula you cannot just plug numbers into this formula. Why not? Why? Because this x represents each number in the sample, okay? So there's 5 numbers in the sample. You can't put 5 numbers in here, okay? The formula is just a symbolic representation of all of these steps, okay? It's just a symbolic representation. It doesn't work where you just plug numbers in and you get an answer out, okay? It's a symbolic representation where this is actually a process that's being displayed. It's showing add them all up once you do this for each number, okay? So you can't just plug numbers in, okay? Yeah. All right, is that okay? Next week on the quiz, you might see a set of numbers and I might say, find the standard deviation of these numbers. And we'll all get 100%, right?
Yes.
Question? I thought I answered this. You are allowed a 3x5 note card with notes, okay? Again, this is detailed on the homework page for this week. Yes?
Front and back?
Are we allowed a calculator?
Yes, you will need a calculator. Not only are you allowed a calculator, you are required to bring a calculator, okay? And next week, again, and I'm very strict about this, if you don't have a calculator, I'm going to say I'm sorry. You're stuck, okay? You are not allowed to use your cell phone as a calculator, okay? You are not allowed to share calculators during the test, okay? Because who's to say you're not passing answers that way either, okay? So you're not allowed to share calculators. You have to have your own calculator. So don't come up to me next week and give me your sob story of how you forgot your calculator in the car or something, okay? Yes?
How many questions is the quiz?
It's a 1-page front and back.
2 pages.
So, I don't know, 5 questions, but there's multiple parts to each question. It's very fair. I've never, you have enough time to complete it, you'll be fine. Yes?
So the 3x5 note card is front and back? Or
Front and back, okay? All of these things can be answered if you look at the webpage. All right, we have another topic to cover before you guys leave, okay? So the standard deviation is especially useful because we can use it as kind of a ruler, as almost like a unit of measure within a data set. Okay, the standard deviation.
God bless you.
Okay. So let me give you 2 examples here, okay? So what if I told you for a certain, I don't know, certain type of tree, okay? Let's say the average branch length is 3 feet, okay? Okay. Let's say I saw an example of this tree, and I say, I saw a tree and its branch length was longer than average, okay? It was 3 feet 3 inches, okay? Would you say, wow, that's unbelievable. I can't believe that tree had a branch that was 3 feet 3 inches. No, that seems like, oh, okay. That seems totally normal, right? I'm telling you the average is 3 feet, okay? But there's something in you that says, oh, so you saw a tree with a branch length of 3 feet 3 inches, no big deal. Okay? All right. Let's say you go to the yardstick factory, okay? And they produce yardsticks. And the average length of a yardstick is what? It's 3 feet, okay? So they're producing yardsticks. The average length of a yardstick is 3 feet. And then I say, you know what? I ordered some yardsticks in the mail. I got a yardstick of 3 feet 3 inches. Okay? What would you say about that?
Yardsticks.
Yeah, you'd say, well, that's unusual. They shouldn't be selling that as a yardstick, right?
Yes, sir.
Okay. What's the difference there? In both cases, we're talking about sticks, and the average length of a stick is 3 feet. But in one case, seeing a stick that was 3 feet 3 inches is not impressive, but seeing a stick that was 3 feet 3 inches in the other case was something we regarded as unusual. Okay? Right. That doesn't work, okay? So yardsticks, okay, the average is 3 feet. Okay? But, so in one case, seeing something, in this case 39 inches, this would be highly unusual. It's possible for a factory, you know, if it's stamping out yardsticks, it's possible for one of them to be 39 inches long, okay? But they shouldn't sell this as a yardstick, right? They should say, wait a second, something here is wrong, okay? 39 inches, this is highly unusual. Okay, not just, okay, well, and part of it is because they're calling them yardsticks and stuff. Okay, but over here, seeing a tree branch of 39 inches, not unusual. Okay, even in both cases, the average is 3 feet. Okay, the thing that's going on is over here, we're expecting a lot more variation, or we're expecting a large standard deviation. Okay, so here there is a large standard deviation. Over here, there is a tiny, there should be a tiny standard deviation. Tiny standard deviation, okay? The amount of spread is very small. The amount of spread over here, very big. Over here, we're expecting the difference from tree branch to tree branch to be quite a bit. Okay, we're not expecting all tree branches to be exactly the same. When we're talking about yardsticks, we're expecting the difference from yardstick to yardstick to be incredibly small, okay? We will probably allow, you know, maybe a millimeter of difference from yardstick to yardstick, but probably not a whole lot more than that, okay? Otherwise, we'll say these are poor quality yardsticks, I don't trust them, okay? And the standard deviation allows us to get an idea of what is something that is unusual or not unusual. So does this overall concept kind of make sense?
No.
No? Who said no? Okay, alright. What's confusing to you? Alright, I don't want to hear that from the other guys. Okay, if a student has an honest question, please treat it sincerely.
I don't know. The whole thing is confusing. Like how is it that for a tree it's normal, but I mean for the tree branch it's normal, but for the yardstick it's not. Isn't the average 3 feet? Why can't you have 39 inches?
Yeah.
So
So at the factory, okay, this is we're producing yardsticks, okay?
Okay.
If we're producing yardsticks at a factory, we're expecting all of our yardsticks to be almost exactly the same length, right? This is the job of the factory to be making these things, okay?
Okay.
So it'd be surprising to get something that wasn't a yard, okay? You know, even if it wasn't, you know, if the factory's producing letter-sized paper, okay?
I got it.
And you get a piece of paper that's way bigger or something or half the size, that would be very surprising, okay?
Okay, thank you.
Okay. So that's what we've got going on, okay? And underlying all of this, okay, so this is intuitive, okay? So I'm trying to tie your intuitive sense of things to the kind of the numeric stuff, okay? So the intuitive sense is that the yardsticks, the one that's much larger than, you know, in both cases you got something that's 3 inches more than average, okay? But in the yardsticks, what's going on is that we're expecting a tiny standard deviation, so when something is 3 inches, that's large compared to the standard deviation. Over here we're expecting a large standard deviation, so a difference of 3 inches from average is not that large compared to the standard deviation, okay?
Thank you.
So let's deal with another situation, okay? I might go a few minutes past 9:30, and I apologize for that, okay? If you gotta go, you know, you can leave, and I will not be offended, okay? All right, so let's say, let's deal with, let's talk about Labrador retrievers, okay? So lab dogs, all right? Labrador dogs. Lab dog sounds like something grown in a laboratory. Okay, so we got Labrador dogs. I don't know. Let's say I'm making numbers up here, okay? But let's say the mean is 50 pounds, okay? I don't know. Who knows, okay? And let's say the standard deviation is 10 pounds, okay? Let's look at like Boston Terriers, okay? And again, I don't know. I'm making some numbers up, okay? But let's say the mean weight of Boston Terrier, they're a lot smaller, right? Let's say is 15 pounds. That sounds good. Okay? And the standard deviation for Boston Terrier, let's say, is 3 pounds. I don't know. Okay, so let's say the other day you see a dog, okay? And it's a 83-pound Labrador. Okay? And you say, wow, that's a big dog. Okay? And then somebody else says, well, you know, I saw a Boston Terrier and it was let's say it was a 27-pound Boston Terrier. Okay? So you're like, oh, well, that's a big Boston Terrier. Okay, so which of these is more unusual?
The Boston Terrier.
Okay, well, this is our intuitive sense. Okay, our intuitive sense says, oh, you know, this fat Boston Terrier, something's wrong with that thing. Okay, but we can use statistics to back this up. Okay, so I'm going to introduce the idea of a z-score. A z-score is how many standard deviations something is away from the mean. Okay, z-score is the number of standard deviations something is from the mean. Okay? So, the Labrador dog, this 83-pound Labrador, how much bigger than the mean is it?
3.3.
It's 33 pounds more than the mean, and how many standard deviations is that? It's 3.3, okay? So a z-score, we can think of it as we take the weight of the Labrador and we subtract off the mean. This gives us how far something is from the mean, okay? And that is, we say this is 33 pounds more than the mean, okay? But we want to know not just how many pounds, but how many standard deviations, okay? Each standard deviation is 10 pounds, so I'm going to take this and divide by 10, and we see that this 83-pound Labrador is 3.3 pounds over, 3.3 standard deviations larger than the mean. Okay, is that okay? Okay, how much would a Labrador be if it's one standard deviation below the mean?
40.
40 pounds, okay? Can you guys see that? If the mean is 50 pounds, one standard deviation less than the mean would be 40 pounds, because each standard deviation is 10 pounds, okay? All right, so don't shout out the answer, but think of it in your head. How much would a Boston Terrier be if it's one standard deviation over the mean? Don't shout it out, just think of it. And the answer is 18 pounds, okay? Boston Terrier is one standard deviation over the mean, it would be 18 pounds, okay? So how many standard deviations is this Boston Terrier away from the mean?
4.
It's
6.
okay. So how many standard deviations? Okay, so the z-score here is the number of standard deviations it is from the mean. So it is 27 pounds, and we subtract off the mean of 15, and I divide by 3, right? So I get 12 over 3. 4. This Boston Terrier has a z-score of 4. It is 4 standard deviations larger than the average Boston Terrier. Okay? And so when we can compare not the numbers, not the weights themselves, but the standard deviation, or the z-scores, okay? So this z-score is 4, this z-score is 3.3. So this one is more unusual than that one, okay? This z-score is larger. So it is more unusual. Alright, is that okay? Okay, you've got a few problems in your homework, going over all of these concepts. Details on the quiz are on the web page, and we'll see you guys next week.